Welcome to this course of building Agentic RAG application. So let's begin with the basics of how to build Agentic RAG applications. So initially in this chapter, we will first begin with what is an agent. So an agent is the context of artificial intelligence referred to a system that autonomously perceives its environment, makes decisions based on the data, and performs actions to achieve specific goals. An agent can interact with its environment, learn from it, and adapt its behavior accordingly. In more complex systems, agents can perform decision-making tasks such as analyzing patterns, making predictions, or even autonomously carrying out tasks based on the context and user interaction. So now, let's understand with the help of an example. A virtual assistant is an agent. When you ask it a question, it perceives the environment, that is the query. It processes the data and provides a response based on the knowledge base. It may also make autonomous decisions such as sending you reminders or scheduling meetings based on your preferences and calendar information. Now let's move on to understand what is RAG. RAG or Retrieval Augmented Generation, it is an AI technique that combines the two approaches to improve the quality of the generated responses. Point number 1 is retrieval. The system retrieves the relevant data from an external knowledge base, database, or document set. Then we have generation, that is the generative model processes the retrieved data to create an accurate and contextually appropriate response. So RAG system enhance the capabilities of generative models by pulling in real-time dynamic data from the external sources. So this helps the system create responses that are more informed, accurate, and relevant to the context. Then let's understand this with the help of an example. So imagine you are building a customer support chatbot. So if the chatbot only relied on its internal knowledge, it would be limited to the information it was initially trained on. But with RAG, the chatbot can query an up-to-date knowledge base and generate a response that includes the latest information available, such as the product updates, return policies, or stock levels. Now let us understand what is Agentic RAG. Now we bring together the concepts of agentic behavior and RAG together. So an agentic RAG system is an AI that not only retrieves the information from the external sources and generates response, but also takes actions based on the information it retrieves and the decisions it makes autonomously. So these systems can go beyond simple answering queries. They can perform tasks, trigger events, and even act on the retrieved data. So agentic RAG systems are designed to be more autonomous, leveraging the full potential of both the data retrieval and the decision making. So let's understand this with the help of an example. So consider a project management assistant powered by Agentic RAG. You ask it to find the next available time for a team meeting. The assistant retrieves the relevant data from your calendar, checks for the conflicts, and autonomously schedules a meeting based on the availability of the participants without needing you to intervene. Now let us understand why are agentic RAG systems used. So agentic RAG systems are valuable because they provide a comprehensive, scalable solution to complex tasks which combines the benefits of both autonomous decision making and data augmentation. So here are the primary reasons why these systems are used. Now let us understand the first one. We have autonomous decision making. They can make informed decisions based on the external data, helping automate processes that traditionally require human oversight, such as scheduling, email responses, or task delegation. Then we move on to the next. We have context-aware responses. By retrieving the real-time information, agentic RAG systems can generate highly relevant, contextual, accurate, and up-to-date responses. Then third, we have task automation. The task automation, these systems can perform a variety of tasks such as sending mails, scheduling meetings, or updating their records based on the retrieved information, which can reduce the need for the human intervention. Now moving on to the last one, we have scalability. Since agentic RAG systems are capable of continuously retrieving external data and using it for decision making and actions, they can easily scale across multiple use cases and environments. Now let us understand what is Llamaindex. So at the core of building agentic RAG applications is the ability to efficiently retrieve data and augment the generative process. This is where Llamaindex comes into play. So Llamaindex, formerly known as the GPT Index, is a framework designed to simplify the process of creating the retrieval augmented generation applications. So it enables the developers to index the large volumes of data from various sources such as documents, databases, or APIs, and use that data to augment the generative models like GPT. So by leveraging the Llamaindex, you can efficiently manage data retrieval, make your generative models more informed, and enable your agentic RAG system to act autonomously based on the real-time information. Now let's move on to understand why we use Llamaindex. So we use Llamaindex for efficient data indexing. So Llamaindex basically allows you to organize and index your data, making it easy to retrieve relevant information based on your queries or system needs. Then we have seamless integration. So it integrates with the generative models like GPT, enabling the real-time data retrieval to enhance the responses. Then we have customizable. That is, Llamaindex is flexible and allows you to define how data is indexed and retrieved, ensuring that it fits your specific application needs. Then it can be scalable. So it can handle the large data sets, which is critical for building applications that need to scale. Now, let's understand how to build this agentic RAG applications using Llamaindex. Now, let's outline the key steps involved in building the agentic RAG applications using Llamaindex. So, these steps will guide you through the process of setting up your environment, indexing your data, and integrating it with an agent capable of autonomous decision making. Now, the first step is setting up your development environment. To begin with this, you will need to set up a development environment that includes the necessary tools and libraries to build an agentic RAG application. The first one is install Python. So ensure you have Python installed in your device, as Llamaindex is built on Python. Then install the dependencies. So use a package manager like the PIP to install the Llamaindex and other necessary libraries like OpenAI if you are using the GPT-based models. Then thirdly, we will set up the API keys. So if you are using the external models such as OpenAI, make sure you set up the necessary API keys for your access. Now the second step is index your data. So the next step is to index the data that your agentic RAG system will retrieve. This could be data from the internal documents, databases, or external APIs. Here's how to proceed. The first one is loading your data. So collect and load the data that you want to index into a suitable format. This could be text documents, CSV files, or the data from an API. Next, create an index. Use Llamaindex to index your data. This involves processing the data to create a structure that can be easily queued. The third one is storing your index. So once the data is indexed, save it in a way that makes it easily accessible for the future queries. Now moving on to the third step, we have implementing the retrieval logic. Now that you have indexed your data, you need to implement the retrieval mechanism. So the goal here is to allow your system to fetch the relevant information based on a user's input or the system queries. Now the first one we have is defining the search queries. So set up logic that can process incoming queries and retrieve the relevant data from your indexed knowledge base. Then we are customizing the retrieval parameters. That is fine-tuning your retrieve processes by defining the parameters for what constitutes the relevant data. For example, by setting the thresholds for similarity or relevance. Now moving on, for the fourth step, we have building the agentic logic. So with the retrieval process in place, you will now focus on implementing the agentic logic that will autonomously act based on the retrieved data. So this is where you define how the system will make the decisions and perform the actions. So the first one over here we have decision making. So implementing the logic that allows your system to decide what actions to take based on the retrieved information. For example, if the system finds that a user needs a meeting schedule, it should be able to autonomously check the calendar, find available times, and book the meeting. Now, secondly comes action. Basically, action handling. So it integrates the external services such as the calendar APIs or email services to enable the system to perform actions like sending messages, scheduling events, or even generating the reports. Now, moving on to the last but not the least step number 5, that is testing and integration. So finally, integrate the data retrieval, generate models, and agentic decision-making logic into a fully functional system. So once integrated, test your agentic RAG system to ensure that it works as expected. So firstly, we will test the data retrieval. So ensure that the system retrieves the collect data in response to use the queries. Then we have test the agentic actions. Verify that the agent takes appropriate actions based on the retrieved data. This could use scheduling tasks, sending notifications, or triggering other processes. Now that we understand all the steps, let us see what are the components of the agentic RAG. So the first component over here is knowledge base. So knowledge base is this external data source from which the agent retrieves information. Now moving on to the second, we have agent. It is responsible for retrieving, processing data, and making autonomous decisions. Then we have retrieval mechanism. So it basically fetches the relevant data from the knowledge based on the queries. Now we have generative model. So what it does process the retrieved data to generate the contextually accurate responses. Then we have action logic. This dictates tasks that agent can autonomously perform based on the retrieved data. And then finally we have router query engine. So the router query engine routes the queries to the appropriate agent or component for the efficient processing. Now after we are aware about the components, let's have a look on the simplified flow of how these components work together to process a query in Agentic RAG system. So the first step they perform is receiving the query. The system receives a user query. This could be a simple question like, what's my next meeting? Or a more complex request like scheduling a meeting with John tomorrow at 10 a.m. Then after this, we're routing the query. The router query engine over here analyzes the query and determines which agent or component is best suited to handle it. For example, it might route the query to the scheduling agent. Then after this, we will retrieving the data. So the assigned agent then triggers the retrieval mechanism to fetch the relevant data from the knowledge base. So in this case, the system might pull the calendar data or check John's availability. Now, let's move on to the next one is processing the data. So once the data is retrieved, the generative model uses the data to generate a contextually accurate response. The generative model may also produce a task description such as scheduling a meeting. After that, we will be executing the action. So the action logic takes over, allowing the agent to autonomously schedule the meeting or take any required action based on the retrieved data and generate response. Now after that, the final move we have is completing the task. The system basically confirms the action. For example, your meeting with John has been scheduled for 10 a.m. tomorrow and delivers the result to the user. So after understanding how to process a query in the Agentic RAG, in the next chapter, let's understand the router query engine in details. So in the world of artificial intelligence and natural language processing, one of the essential components of an effective AI system is the router query engine. But before we get into the details of the router query engine, let's break things down in simple terms. So initially we'll understand what is a router. Imagine you are in a large airport and you have to catch a flight. There are many different flights going to different destinations, and you need to know which gate you should go. The router in the AI system works in a similar way. It's responsible for directing the user queries or the questions or the prompts to the right system for processing. To make it easier, we'll understand a router actually listens to the user's questions or request. Then it figures out the best way to handle that question, whether it needs to look up the facts, generate the creative responses, or something in between. Then we will finally route the query to the appropriate system to get an answer. Think of router as the traffic controller that ensures each question goes to the right place. Then we will understand what is a router query engine. The router query engine is a system that uses the router to manage and handle the user queries efficiently. It's like the brains behind the traffic controller. It makes decisions about where to send each query based on the nature of the request. In more technical sense, the router query engine is a key component of the Agentic Retrieval Augmented Generation framework. The RAG system combines the two main technologies, the retrieval-based system and the generative system. So now, a router query engine helps decide whether a query should go to a retrieval system, that is to get factual answers from a database, or a generative model to create the creative content like stories or summaries, or a combination of both. Now let us understand why is the router query engine so important. So the router query engine is crucial for several reasons. So it is crucial for the efficient query management. So without the router, the system would be losing trying to process all the kinds of queries the same way. For example, a question like what is the capital of France needs a simple factual answer. So it should go to a retrieval system. So a question like write a poem about the ocean needs a creative generation. So it should go to the generative model. Now moving on to the next, we have improving performance. The router query engine improves the system performance by ensuring each query is processed in the most efficient way. It reduces unnecessary work and speeds up the response time. Now moving on to the third one, we have increases accuracy. So by sending queries to the right system, the router ensures that responses are more accurate and relevant. So it helps avoid sending creative tasks to a factual system or vice versa. So fourth, we have scalability. So as systems grow and new types of queries or models are added, the router query engine can easily be adapted to handle new kinds of queries or responses without much reconfiguration. Now let us understand how does the router query engine actually work. So let's break down the processes into simple steps. So the first step we have is receiving the query. So the router query engine receives the user's query or prompt. This could be anything like what is quantum computing, or write a poem about the sea, or summarize the latest AI research. Then moving to the second step, we have classifying the intent. So once the router receives the query, it classifies the query to determine what kind of response is needed. The classification process identifies whether the query needs a factual information, that is like definitions, dates or facts, or summarization, that is like considering an article or research, or generative responses, that is like creative writing, opinions or complex explanations. Now moving on to the third step, we have routing to the right system. So after classifying the query, the router decides where to send the request. The first one is factual retrieval. So if the query is factual, for example, what is the capital of France? The router sends it to a knowledge-based retriever which looks up the correct answer from a database. Then we have generative model. So if the query requires creative or free generation, for example, write a poem about the sea, the router sends it to the generative model like the GPT or other AI models that can create content. Then we have hybrid approach, that is sometimes the query needs both factual and creative elements. Like tell me how AI is used in healthcare. The router can send part of the query to a retriever and another part to a generative model. Now moving on to the fourth step, we have returning the response. So once the query is routed to the right system, the system processes the query and generates a response. The router then sends the response back to the user. So example of a router query engine in action. So let's work through some examples to see how the router query engine actually works in. For example, we have one factual query, and what the query is, what is the capital of France, as we have seen earlier. So the router's action can be the router detects that this is a factual query and routes it to the knowledge-based retriever. Then the response would be the knowledge-based retriever looks up the answer and returns the capital of France is Paris. Now let us see all this in action. So the line from the helper import get open API key imports a function called the get open API key from a module named helper. So the next line open API key is equal to get OpenAI API key calls this function to retrieve the OpenAI API key and stores it in the variable OpenAI API key for the later use in the program. So this code is essentially setting up the API key needed to interact with the OpenAI's services. So let's run this. Now the next code is about import nest SNCO imports the nest SNCO library, and the nest SNCO apply allows running asynchronous code in the environments like Jupyter Notebooks where an event loop is already running. It enables the nested event loops, making it possible to run the async functions without conflicts. So now here, the code from Llamaindex.core import simple directory reader imports the simple directory reader class from the Llamaindex library, especially from the core module. So the simple directory reader is used to read and load documents from a specialized directory or the set of files. So the next line you can see documents simple directory reader input files equal to metagpt.pdf.load data. The simple directory reader is being used to load a document. In this case it is metagpt.pdf. So simple directory reader, if I tell in a broad way, input files equal to metagpt pdf, this part creates an instance of the simple directory reader class and specifies the file metagpt.pdf as the input file. So this means that the reader will load data from the particular PDF document. Then coming to .load data, this method is called on the simple directory reader instance, basically to read and load the data from the specified file. Here in this case it is again metagpt.pdf file. The resulting data is then stored in the variable documents, which will now contain the contents of the metagpt PDF file ready for further processing. So in simple terms, the code is used to load a PDF file into the program so that its contents can be used or processed for further use. So here basically from Llamaindex code .node parser import sentence splitter, we are importing the sentence splitter and then we are storing the sentence splitter in a variable known as splitter with a chunk size mentioned as 1024. Then we are splitting the documents splitter.get nodes from the documents, and then we have calling the documents over here. So we'll run this. So here basically the code imports essential components from the Llamaindex library to configure models for the text generation and embeddings. The settings class is used to configure the system. The OpenAI class is imported to handle the text generation with the OpenAI's GPT 3.5 Turbo model, while the OpenAI embedding class is used to generate the text embeddings with the text embedding ADA002 model. The line settings.llm is equal to OpenAI model is equal to GPT 3.5 Turbo sets the language generation model to GPT 3.5 Turbo, so which is used for generation human-like text. Similarly, settings.embed model is equal to OpenAI embedding model is equal to text embedding adder 002 configures the system to use the text embedding adder 002 for creating numerical representations that are known as embeddings over here of text. So this setup prepares the system for handling both text generation and semantic analysis tasks effectively. So here basically the code creates two types of indexes using the Llamaindex library. So the summary index is this index organizes the nodes, that is the data chunks, for efficient summarization, making it easy to retrieve the concise information from a collection of data. Then we have vector store index. So this index stores nodes as a vector representation also known as embeddings, allowing for similarity searches based on the semantic meaning. So both indexes are designed to enable the fast and efficient data retrieval. Summary index for summarization and vector store index for similarity-based queries. We'll run this. So here in this code, the code creates two query engines, the summary query engine and the vector query engine. So the summary query engine basically converts the summary index into a query engine that returns the summarized results in the tree structure and processes queries asynchronously for faster performance. But the vector query engine, it converts the vector store index into a query engine for performing similarity-based queries using the vector representations of the data. So these engines enable efficient querying for summarized or semantical similar data. Then we'll run this. So this code creates the two query engine tool objects. For example, the summary tool and the vector tool. So each serving a specific purpose for querying the data. So the summary tool is used for the summary query engine to handle the summarization related queries about MetaGPT. It is designed to provide the concise summaries when users ask for general information or overviews related to the MetaGPT. The description that is given over here that is useful for summarization questions related to MetaGPT, it basically clarifies that this tool is specially built to assist in summarizing the content. Then we have vector tool. So this tool uses the vector query engine to retrieve the specific content from the MetaGPT paper. So by leveraging vector-based similarity search, it can find and provide the contextually relevant information based on the semantic meaning of the user's query. The description that is useful for retrieving specific context from the MetaGPT paper highlights its use for the context-based retrieval. So these tools are essential for providing users with the targeted responses, either summarizing large chunks of data or retrieving the specific contextually relevant information from the MetaGPT paper based on their query needs. Here next, the code creates a router query engine to route the queries to the appropriate tools based on the query type. So it uses LLM single selector dot from defaults. This selector helps the router decide which tool to use for a query. Then we have query engine tools, that is summary tool, vector tool, that is given in brackets. So these are the two tools that the router can route queries to. The summary tool handles the summarization queries and the vector tool handles the contextual retrieval based on vector similarity. Then we have verbose is equal to true. So this enables detailed login to track the routing process and query handling. So the router query engine over here routes queries to the correct tool based on the type of query, with the LLM single selector helping make the decision and verbose providing helpful logs for transparency. So here I have the first response, the query engine.query, what is a summary of the document? So this line sends the query, what is a summary of the document, to the query engine, which is the router query engine set up earlier in the codes. The engine will route this query to the appropriate tool based on the query type. Since this is a summarization query, it will likely to be routed to the summary tool, which provides the summarized information related to MetaGPT. So we will run this. And now, basically, it is done. So now we'll see the result. Print str, then we will pass the response. We'll run this. So now the response from the query engine is stored in the response variable. So this line then converts the response into a string if it is not already and prints it to the console, displaying the summary of the documents. So see, this is the summary of the response. Then let's see the length of the source nodes. Length, then we'll see response dot source nodes. We'll run this and we'll see as 34. So what this line is basically doing, this print length response.source node prints the number of data pieces or the nodes that contributed to the response. The source nodes represent the part of the document or data used to generate the answer, and the length that is calculates how many nodes were involved, and printing it shows how many sections or chunks were used to create the response. Then move on to the next response. So here in the next response, we have this line sends a query, how do agents share information with other agents, to the query engine, which is the router query engine. The query engine will process the question similarly as I have done above and route it to the appropriate tool based on the query type. So in this case, since the query is asking about how agents share information, it will be routed to the vector tool or the summary tool depending on the configuration, which will use the relevant information to generate an answer. And finally, we are printing the response returned by the query engine. So we'll run this. So it is showing selecting the query engine 0. The choice is more relevant as it pertains to summarization questions related to the MetaGPT. First it processes, then it shares the result. Now after seeing all these responses, let's put all this together and then again run the previous what we have run it. And then finally we have given one response. The code sends the query, tell me about the ablation study results, to the query engine, which processes the questions again based on the content of the document metagpt.pdf. The query engine routes the request to the appropriate tool, retrieves the relevant information and stores the result in the response variable. So the line print str response basically converts the response into a string if needed, as I have already explained. I'm actually concluding it. And then prints it displaying the answer about the ablation study results based on the information that is there in the PDF. So let's run this. So the ablation study results show that MetaGPT effectively addresses challenges related to the context utilization. So that is it for this lesson. Down the line you will see the next chapter of tool calling. So in this lesson, we will explore how an AI agent using a language model can not only choose a function to execute but also figure out the arguments needed for that function. So this concept is a part of the larger process of tool calling and agentic retrieval augmented generation applications, which significantly enhances the AI's capabilities. So let's begin with what is tool calling. So tool calling refers to the agent's ability to dynamically invoke the external tools such as APIs, databases, or the specialized functions to retrieve, process, and generate the responses effectively. This is critical in the RAG systems where the agent may need to access the real-time data or the structured information that is not contained in the model's training data. Now let's move on and understand why is tool calling so important. So in a traditional model, the AI's knowledge is static and based on the data it was trained on. So tool calling adds a layer of dynamism, allowing the agent to fetch up the data information, perform calculations, and interact with the external systems to answer the complex queries. So this makes the agent more adaptive and capable of answering the questions accurately even if the data is not present within its original training set. Now let's move on and understand how tool calling works in the RAG applications. So tool calling in RAG applications typically follows a structured pipeline where the AI agents decides when and how to retrieve the external information and execute the specific function. So let's break it down. So the first one is user query processing. The process begins when the user submits a query. So the AI system analyzes the question to determine if it can be answered with the internal knowledge or if it needs to fetch the external data. So if the query requires the real-time information, for example, the current weather or the stock prices, or the structured data, for example, the SQL queries or the API calls, the agent prepares to invoke the external tools. For example, a query like what's the latest news on AI would require a tool to call to fetch the live news updates from an API. Now next we have retrieve and augmentation. So once the system decides the external data is needed, it chooses the appropriate retrieval mechanism. So the common approaches include semantic search using vector databases like the Pinecone, FAISS, or the Vevit to retrieve the documents based on their meeting. Now, second, we have SQL or NoSQL queries to retrieve the structured data from databases. Then we have API calls to fetch the real-time information such as the weather data from OpenWeather or the stock prices via financial APIs. So this stage helps augment the model's response with the latest and the most relevant information, enhancing the accuracy of the generated answer. Then we have processing and validation. So after retrieving the data, the system must ensure the information is accurate and relevant before using it in the response. For example, if multiple documents are retrieved, the system ranks them by relevance, their meaning. So it might also summarize the large amounts of data or deduplicate the conflicting information. So if the query requires calculation, for example, what's the 10% of $2,000, the system can execute a Python function to perform the calculation and include the result. So this processing step ensures that the data being used is valid and useful for the final answer. Then we have final response generation. So once the information has been validated, the system generates the final response. The large language model then combines the agent's internal knowledge with the retrieved data to craft a coherent and a concise answer. The response is formatted in a user-friendly way, making it easy to understand. So if there is any conflicting information, the agent may provide multiple perspectives or the site's resources. So now let's move on to understand how tool calling makes RAG more powerful. So tool calling adds a dynamic element to the model, allowing it to access the real-time data. So the agent can call APIs to get the latest information such as the stock prices or the news updates. Then we have execute the complete task. For example, it can perform calculations, run queries, or interact with the external databases. Then we have validate and refine process. So the agent can cross-check multiple data sources and remove redundant information, ensuring the accuracy of the final response. So this makes the RAG system more autonomous and capable of handling complex real-time queries, particularly in the domains like business intelligence, customer support, and research. Now to make all this clear, let's look at a demo. We are now going to show you how a RAG system with tool calling works in practice. So the demo will highlight how the agent can use the external tools like the APIs or database to fetch data that is not only a part of its internal knowledge base. So it also will show the use of the retrieved data to enhance the response generation, making the final answer more accurate and dynamic. So in the demo, you will see how the agent dynamically calls tools based on the query type, whether it's for the real-time information, structured data, or performing the specific functions like calculations. So, in this line, the helper module is assumed to be a Python file, likely called the helper.py. that contains the various utility functions. The getOpenAI API key function is specially designed to retrieve the OpenAI API key, which is needed to authenticate the request to the OpenAI services such as GPT models or other AI-based services. So by importing this function, you can call it to fetch the API key without needing to hard code it directly in your script. So next, the code calls the getOpenAI API key function and assigns it to the return the value OpenAI API key variable. So this line invokes the getOpenAI API key function, which likely retrieves the API key from a secure source, such as environment variable, configuration file, or a secrets management system. The retrieved API key is then stored in the OpenAI API key variable. The key is crucial for making the authenticated request to the OpenAI services. So by storing it in a variable, you can easily use this API key throughout your code to authenticate your various OpenAI related operations. Make sure to get yours. We'll run this. Then we'll import. The Nest Asensio library is a Python package that allows you to Asensio, Python's built-in library for writing asynchronous code in environments that already run in their own event loop, such as the Jupyter notebooks. So by default, Asensio does not always allow nested event loops, meaning you cannot run as Asensio event loop inside another event loop. So however, in interactive environments like the Jupyter notebooks, this limitation can be problematic because they run often an event loop for managing interactions. The Nest Essential package provides a workaround for this, allowing the nested event loops to function without errors. So the code calls apply method from the Nest Essential module. So what does an apply method does? The apply method modifies the behavior of the Essential event loop. It patches the existing event loop to support the nested event loops, which is useful in environments which is useful in environments like Jupyter Notebooks, where you might want to run asynchronous code inside another running event loop. Essentially, calling apply makes it possible to run the multiple asynchronous tasks simultaneously without encountering conflicts or errors due to the nested loops. So we will run this. So here basically we are defining a simple tool. So the function tool is a class provided by the Llamaindex framework, which is used to wrap the regular Python functions into tools that can be integrated into a larger system. So this enables functions to be executed as a part of a broader process, such as the document processing, querying, or other tasks within the Llamaindex ecosystem. The function tool class essentially transforms a standard Python function into a tool that can be used in the context of an agent's workflow. The add function takes two integer arguments, that is the x and y, adds them together and returns the sum. So this function is simple and demonstrates the basic functionality with a clear type annotation indicating that it takes two integers and returns back only one integer. The mystery function, on the other hand, is slightly more complex. It also takes two integers x and y, but instead of just adding them, it first adds the number together and then squares the result by multiplying the sum by itself. So this function is designed to show how more complex operations can be wrapped into tools. We have function tool dot from the defaults, that is fn is equal to add. This line basically wraps the add function into a function tool object, making it available for use in the Llamaindex framework. The from defaults method configures the tool with the default settings and associates it with the add function. Then we have function tool from the defaults fn is equal to mystery. Similarly, this line wraps the mystery function into a function tool, allowing it to be used as a tool in the framework. So this tool can be applied to more complex workflows or the agent task. So both the add tool and the mystery tool are now instances of the function tool, and they can be integrated into the Llamaindex agents or other systems, making the function modular and reusable. So we will run this. Here basically this import allows the script to interact with the OpenAI's models such as the GPT 3.5 within the Llamaindex framework. So by importing the OpenAI class, the script gains the ability to use the OpenAI's language models to process data and generate responses in a structured way, facilitating the tasks like task generation, summarization, or the question answering. So next, the code initializes the instance of the OpenAI class. So here the OpenAI class is instantiated with the model GPT 3.5 Turbo argument, specifying that the script will use OpenAI's GPT 3.5 Turbo model. So this model is a powerful version of GPT 3.5, known for being both efficient and cost effective. The LLM object represents this instance of the OpenAI model, which will be used to perform tasks such as generating predictions and responses based on the provided input. The following line calls the predict and call method on the LLM object. Response is equal to LLM.predict and call, add tool, mystery tool, and everything verbose is equal to true. So predict and call, this method allows the LLM to use the provided tools, that is the add tool and the mystery tool, and perform a task based on the given input. So in this case, the input question asks for the output of the mystery function when applied to the numbers 2 and 9. Basically, add tool and mystery tool, this is a list of tools, add tool and mystery tool, and that the LLM can use to generate the response. So these tools were defined earlier in the code and wrapped the add and mystery functions. Tell me the output of the mystery function on 2 and 9. So this is a query being sent to the model. The agent will process the request using the mystery tool to calculate the result, applying the mystery function to 2 and 9. Then verbose is equal to 2. This argument enables the detailed logging, which helps track the internal operations and the steps the agent takes to generate the response. Finally, the code prints the response by converting it into a string. there is a print response. And now you can see the function output is 1 to 1 and it's nice. So the code begins by importing the simple directory reader class from the Llamaindex.core module. So simple directory reader is a class provided by the Llamaindex framework which is designed to load and process the documents from the files or the directories. So the class helps in reading documents such as the PDF, text files or other supported formats and prepares them for further processing or indexing in the Llamaindex system. So by importing the simple directory reader, you are setting up a tool to load the documents into your program, enabling them to be used for tasks like text analysis or information retrieval. So next the code creates an instance of the simple directory reader and loads the documents. Then we have simple directory reader input files equal to metagpt PDF. So this line initializes the simple directory reader with the input files parameter which specifies the files to be loaded. In this code, the code is loading in a single file, that is metagpt.pdf, located in the working directory. You can specify the multiple files or an entire directory if needed, and the reader will load them accordingly. Then basically we are loading the data with .load data. After initializing this simple directory reader with the list of the files, the load data method is called. This method reads the content of the specified files and processes the data. It then processes and reads metagpt.pdf document, extracting the text or data it contains and preparing it for use in the further task. The result is then stored in the documents variable, which now contains the loaded data from the PDF file. So which now will run this. So here basically sentence splitter is a class in the Llamaindex framework that helps in splitting the large documents into smaller manageable chunks. So this process is useful for tasks like document indexing, where breaking down documents into smaller pieces allows more efficient querying and data processing. So by importing the sentence splitter, the code is setting up a tool that will take large documents and divide them into smaller chunks, often at the sentence level, which can then be processed further or indexed. Then sentence splitter chunk size equal to 1024. The sentence splitter class is initialized with the chunk size parameter set to 1024. So this parameter specifies the maximum size in terms of token count for each chunk of text that the splitter will create. So in this case, each chunk will contain up to 1024 tokens, which typically corresponds to a certain number of words or sentences depending on the language model's tokenization process. So by setting this parameter, the code is instructing the sentence splitter to split the document into smaller sections that can be processed more efficiently, ensuring that no chunk exceeds the specified size. The nodes variable will contain the resulting smaller chunks, which can now be used in further processing, such as building a document index or answering the questions efficiently. Then finally, the nodes help improve performance by allowing the system to work with the smaller pieces of data rather than processing large documents all at once. So we'll run this. So nodes 0 accesses the first chunk of the text in the nodes list, and .get contain metadata mode equal to all retrieves the full content of the node, including all the metadata such as the source, timestamp or other details. Then it prints the output of the content to the console and will run this. And now you can basically see the page label, the preprint with the metadata and everything. So here basically the vector store index is a class in the Llamaindex framework that is used to create an index of the vectors. So this class allows the efficient storage, retrieval and the querying of the document data represented as vectors. So the vector store index enables the efficient querying of these vectors, making it ideal for searching or retrieving information based on the vector similarity. So the vector store index, there is the nodes. This line initializes the vector store index object using the nodes as input. The nodes represent the smaller chunks of the text from the previous step, and this index will store their vector representation. So each node, that is a text chunk, is converted into a vector using methods like the embedding models, which can represent the text numerically, allowing for efficient similarity searches. The vector index now holds this vector's representation, enabling the quick access to them for querying purposes. Then we have vector index dot as query engine similarity top k is equal to 2. This method converts a vector index into a query engine. This can be used to retrieve information from the vector index. The similarity top k is equal to 2 parameter specifies that when querying, the engine will return the top 2 most similar vectors based on the similarity of the query to the index vectors. The query engine now allows for querying the vector index to find the most similar nodes, that is a text chunks, to a given query based on the similarity. So here basically the metadata filters is a class provided by the Llamaindex that allows you to filter the query results based on the metadata associated with the documents or the nodes in the index. So metadata filters makes it possible to refine the search results by applying filters that restrict the query to specific metadata values. Then we have similarity top k is equal to 2. This parameter specifies that the query engine should return the top 2 most similar results based on the vector similarity between the query and the index nodes. Then we have filters, metadata filters from the directories. The filter parameter is used to apply the metadata based filtering to the query. The metadata filters dot from the directory takes a list of the dictionaries where each dictionary contains a key and a value. In this case, the filter is looking for the nodes where the page label metadata is set to 2. So with these settings, the query engine will not only find the most similar vectors but will also ensure that the results are filtered based on the metadata page label equal to 2. Then we have query engine dot query. What are some high level results of MetaGPT? So this line sends the query what are some high level results of the MetaGPT to the query engine. The engine will process the query by searching for the nodes that are most similar to the query text. And then while also adhering to the metadata filter that is only considering nodes with the page level metadata equal to 2. The result of the query is stored in the response. Then after processing, we will print the result. Print str, we have response. So what it does basically? So the code converts the response object into a string using the str as we have discussed previously. So see, it has printed the response. Now here in response.source nodes, this refers to the list of the source nodes that we are used to generate the response. So each node represents a chunk of data or a document that contributed to the response generated by the query engine. For n in the response.source node, this loop goes through each source node in the list of source nodes. So each node, that is n, contains both the content and the metadata that we were used to produce the final response. Then we are finally printing n.metadata. For each source node, the code accesses its metadata and prints it. The metadata could include any additional information and make the node such as the source document's title, author, page level or any custom attributes attached to the node. Printing the metadata allows you to understand the context or origin of the data that contributed to the response. So after this output, we have this code. Don't worry, I'll explain. So list, this is used to specify that the page numbers parameters will be list of strings. It allows the function to accept the multiple page numbers as an input. Then we are coming to filter condition. This is basically an enumeration provided by the Llamaindex that is used to specify how multiple filter conditions should be applied when querying the index. The condition can be AND, where all the conditions must be true, or where at least one condition must be true. Then we have vector query. So this function is designed to perform a vector search over an index based on a provided text query and an optional list of page numbers. The query parameter represents the search query as a string that will be embedded and used for the vector-based similarity matching. The page number parameter is a list of page numbers or strings. It is used to filter the search results by specific pages. So if the list is empty or not provided, the function will search across all pages. Then we have vector query. So this function is designed to perform a vector search over an index based on a provided text query and an optional list of page numbers. So the query parameter represents the search query as a string that will be embedded and used for vector-based similarity matching. The page numbers parameter is a list of page numbers or strings. It is used to filter the search results by specific pages. So if the list is empty or not provided, the function will search across all pages. Then we have metadata directories or dictionaries. This list comprehension creates a list of dictionaries where each dictionary contains a key value pair representing a metadata filter. The key is page level and the value is each number provided in the page numbers list. So these dictionaries are used to filter the search results by the specified page numbers. Then basically we have vector index as query engine. This method converts the vector index into a query engine. The similarity top k is equal to 2. As discussed previously, this specifies that the query engine should return the top 2 most similar results based on the vector similarity. Then we have filters equal to metadata filters dot from the dictionaries. This applies the metadata filters to the query. The metadata filters dot from the dictionaries method creates the filters using the metadata dictionaries generated earlier, and the filter condition .or ensures that the query engine will return results where at least one of the page levels matches any of the specified page numbers. Then basically we have the function tool dot from the defaults, and this method wraps the vector query function into a function tool, making it usable using a larger Llamaindex workflow. So here the code starts by initializing an OpenAI model using the OpenAI class with the GPT 3.5 turbo model and a temperature setting off to 0. So this setup ensures that the model generates the deterministic responses, making it ideal for the consistent and the accurate outputs, especially for the task requiring precise information. Next, the predict and the call method is invoked on the LLM object, passing the vector query tool and a query about the high-level results of the MetaGPT on page number 2. The verbose equal to true argument enables the detailed logging, which provides insights into the query execution process. The resulting response, which contains the relevant high information, is stored in the response variable for further use. That's now you can see MetaGPT achieves a new state of the art, that is a SOTA, in the code generation benchmarks with 85.9% and 87.7% in the pass @ 1. So now, this refers to the list of the source nodes that contributed to the final response generated by the query engine. So each source node represents a chunk of data that was a part of the search processes. The response object contains the agent to generator. The response object contains the output of the query, which could include text, metadata, or other related information derived from the index documents. So let's run this, and you can basically see the page level, file name, file path, and everything that metadata consists of. So here's basically we are adding some of the other tools here, and we are importing the summary index, importing the query engine tool from the llamaindex.core. Then we are passing these nodes in the summary index, and then we are creating the response mode as tree summarize and use async is equal to true. So then we are using one description that is useful if you want to get a summary of the MetaGPT. So we'll run this. So here basically we are passing one response. What are the MetaGPT comparisons with the chat dev described on the page 8? And we are creating a verbose is equal to true. Now you can see basically it is given one function output. MetaGPT outperforms ChatGIF on the software development dataset in the various metrics. For example, basically it has given the answer to this particular question. For now, let's again see the metadata over here and print it. So page level is equal to 8, and we have asked for the described on page 8. So it is correct only. Page level is equal to 8. File name is metagpt.pdf, file path, and everything that we can actually need. Last but not the least, we'll ask something different. What is the summary of the paper? And I hope it gives the correct answer. The paper does not discuss the impact of the climate change on the biodiversity and ecosystem. So we can now see it has not been able to provide the summary of the paper. So for now, we will actually help this out in the next lesson and we'll find the correct answer to this. So let's move on. In simple terms, what you are learning is how to handle your complicated questions that involve multiple steps. Right now, you ask a question, we simply pick the right tool and get you the answer in one go. So however, if the question is more complex with several parts, there needs to be a more structured process to break it down into manageable steps. To explain this concept more thoroughly, let's break it down into the key subtopics and go into detail for each one. So these subtopics will cover the understanding of agent reasoning loops, the functional calling agents, handling the complex queries, and building intelligent agents. Now let us understand what is an agent reasoning loop. So an agent reasoning loop is the process by which an intelligent system handles a complex task or question by breaking it down into smaller logical tasks. So instead of solving the entire problem in one go, the system processes each step sequentially, adjusting its actions based on the previous outcomes. So this makes it much better at handling the intricate, multifaceted problems that cannot be solved in a single forward pass. So now let's see the steps in reasoning loop. The first step is input reception. So the system first receives the query or the task. Then the step is problem breakdown. So the system analyzes the query, identifies the different parts of the problem and organizes them into manageable chunks or steps. The third one is action selection. So the system decides what action or tool to use for each chunk. This can involve calling a specific function, gathering data, or making an interference. Then comes processing and evaluation. The system processes the chosen actions and evaluates the results. Then comes reiteration. So based on the outcomes, the system may revisit the earlier steps to refine or adjust the solution. Then comes what is functional calling agent. So a functional calling agent is an agent designed to work directly with the various functions or tools. So these agents don't simply pass queries to the right tool. They call functions to perform the specific task as a part of solving a larger problem. So this allows the system to integrate multiple processes, ensuring each function is used in the most efficient way for a given subtask. Now let us understand how does it work. So it works in direct functional calls. So instead of a general tool selection process, the agent can call specific functions in a structured way. For instance, it can call a function to fetch data, then another function to process the data, then another function to actually visualize it. Then comes subsequence of actions. So each function call is a part of a planned subsequence of operations that leads to the final solution. This makes the agent much more adaptable and able to handle tasks that require complex steps. Now moving on to the advantages of functional calling agents. So the first one is efficiency. So functions can be reused across tasks, making the agent more efficient. Then comes modularity. Tasks can be broken into smaller, well-defined functions, making the system more maintainable and flexible. Now, moving on, we have scalability. So the agent can call more complex or additional functions as needed without disrupting the overall system. Now, let us understand what makes a query complex. So a complex query is one of the requires multiple steps, involves data from various sources, or has independent parts. For example, a question like what was the company's revenue last year and how does it compare to the same quarter in the previous years involves gathering historical data, performing calculations, and comparing results. A complex query often has conditions, dependencies, and requires dynamic problem solving. So now let's move on to the steps for handling the complex queries. The first one is query decomposition. So the first step is to break down the query into manageable subqueries. For example, if the query involves multiple comparisons, the system will extract the individual comparisons as a separate task. Then is tool and function selection. So each subquery might require different tools or functions. For example, retrieve financial data might require a web API call, while performing a comparison might involve a statistical function. Then we have iterative problem solving. So the agent must evaluate results after each subquery is processed. So if the query's outcome depends on multiple factors, the agent might need to go back and adjust the previous steps. Now let us understand with the help of an example of a complex query. So predict the sales growth for the next quarter based on the sales data of the last 3 quarters and compare it with the trends from the same period last year. So in this example, the step 1 is fetching the sales data for the last 3 quarters. Step 2 would be analyze the sales data to identify the trends. Step 3 is use statistical models to predict the future sales. Then step 4 is fetch data for the same period last year. And finally, compare this year's prediction with the last year's performance. So the agent would need to intelligently move through each step, adjusting based on new information and potentially revisiting the earlier steps if the data is not sufficient. Now let's see all this in action. So far, our queries have been done in a single forward pass. Given the query, call the right tool with the right parameters and getting back the response. So what if the user asks a complex question consisting of multiple steps or a question that needs to be answered in detail? So in this lesson, you will learn how to define a complete agent reasoning loop instead of the tool calling in a single shot setting. An agent is able to reason over tools and multiple steps. You will use the function calling agent implementation, which is an agent that natively integrates with the function calling capabilities of large language models. So we will start and begin with setting up the API key. So after we have completed importing this open API key, we'll import nest SNCO and we'll run this. So for now, we are using the MetaGPT paper as the 2 previous lessons. So we will now set up the function calling agent, and we are using GPT 3.5 Turbo as discussed before, and we are mentioning the temperature is equal to 0. So let's run this. So here, then we import the function calling agent worker from Llamaindex and also the agent runner. And for the function calling agent worker, we pass 2 tools, the vector tools as well as the summary tool. We also pass the LLM and set the verbose equal to true to look at the intermediate outputs. So here basically we are going to ask the first question. Tell me about the agent roles in MetaGPT and then how they communicate with each other. So let's give this as a question. So if we look at the output now, we see that the agent is able to break down this overall question into steps. The first part is asking about the agent roles and the MetaGPT, and it calls the summary tools to answer this question. So now let's look at the content of the first page. So this is the printing the first source model, and we are taking the metadata mode is equal to 1 because we want metadata from each of the responses. So this allows you to, for instance, inspect the content of the first source node that's retrieved. This is the first paper we have given, and here we are using the agent.chat for the first time. The question is about the evaluation of the datasets used. So we will run this. It may take some time to generate. So here if you see, it is basically added user memory to the about the message, tell me about the evaluation datasets used, and it is calling the function, the summary tool MetaGPT with arguments input it is taking. The evaluation datasets used in MetaGPT include the human evil, it is giving the correct response, and even the LLM responses. The evaluation datasets used in MetaGPT include the human evil, MVP, and software development. So we are going to see the next question. So instead of query, we will do agent.chat. The first question was about evaluation. It is about the results over the above datasets. So let's run this. Now basically you will see an example of this ability to maintain the conversational history because we will ask a follow-up question. So these are basically separated: calling function, function output, and the LLM response. The function output and the LLM response must be same. So we will start by defining our agent again through the function calling agent and as well as the agent runner setup. So then we started using the low level API. We'll create a task object over here and user query. Then we'll start running through steps for even injecting our own. Okay. So here we are even passing the agent worker through this agent runner function. So now let's start with executing a particular step of this task. We are using the same lesson as we have used in MetaGPT and let's see this. The question is, tell me about the agent roles in MetaGPT and then how they communicate with each other. So I'll give this input and then let's try a single step of the task. We'll call a .run step task .task id and we'll run this. So it is basically executing and it has added user memory and there's one calling function that is summary tool MetaGPT with the arguments. It is basically taking one input and the agent roles in the MetaGPT. The function output is the agent roles in MetaGPT include the product manager. It is basically giving the output and it is even correct. So previously we can see that it calls the summary tool with the input agent roles and MetaGPT, which is the very first part of this question, and then it stops there. So here in the completed steps, when we inspect the logs and the output of the agent, we see that the first part was actually executed. So we call the agent that completed steps of the task ID and we are able to look at the number completed for the task. So let's now move on to see the upcoming steps of the task. So now we can also look at the upcoming steps. We can do this through agent to get upcoming steps. Again, if we see the output, we pass the task, that our task ID and to the agent and we are able to print out the number of upcoming steps for the task. Now basically we will move on to run the next two steps and actually try and drafting the user input. And here are the next two steps. We can see that we have added that to our user memory and the next call is how agents actually share information and they can actually give back the response. So the function output is agents in MetaGPT share information through a structured communication protocol. This is basically taken as an input how agents share information in MetaGPT and this is basically what they have returned as a response. So this is basically the last step and we will run this. So here we are directly getting the LLM response and it is basically agents in MetaGPT share information through a structured communication protocol. So the overall work is done over here and we just need to return one final step to synthesize the answer. Now to double check that, we can see that we are able to get back the answer about how agents in MetaGPT share information and it is the last step. Now the last step is finalizing this agent and passing the task ID through this and we'll run and then print the response. And we'll run this. Now to finalize it, we will perform the final step and in the next lesson we will show you how to build an agent over multiple documents. Let's move on. So we'll start with setting up the OpenAPI key. We'll run this. And the next, here we will import the nest SNCO and then the first task is to set up our function calling agent over the 3 papers. So we do this by combining the vector summary tools by each document into a list and passing it to the agent so that the agent actually has 6 tools in total. So here we have downloaded 3 papers from the clear. This includes MetaGPT for the last time and it also includes the long loader as well as self-RAG. Next we'll convert each paper into a tool. So this is basically a helper function, gap-doc tools, which automatically builds both a vector and an index tool as well as a summary index tool over a given paper, and the vector tool performs the vector search and the summary tool performs summarization of the entire document. So for each paper we are getting back both vectors and summary tools. So see, it's generated and we got the 3 tools for 3 papers. Next we will simplify get these tools in a flat list. So we'll run this. Next here we are defining 3.5 Turbo from OpenAI and LLM as of our own choice. We'll run this. So now, if we quickly take a look at the number of the tools that are going to be passed to the agent, we will get 6. Because we have 3 papers and 2 tools for each paper, a factory and a summary tool. So let's check. Length of the initial tools. Yeah, 6. So it's giving the right answer. So the next step is to construct our overall agent worker, and it includes all the 6 tools as well as the LLM that we pass out. And we are able to ask questions across these documents or within a single document. So here now we run the code. So for now, let's ask a question about give me a summary of both the self-RAG and the long LoRa. So let's run this. So it's given added user message to the memory, given a summary of both self-RAG and long LoRa. Calling function of the output, it is about self-RAG. Function output is about long LoRa. So it's nice. So now, we have got the answer that one of the eval data sets used is feature 19 test plate. We are able to look at the eval results for our long haul models. So let's see the response, okay? We print it. Print str and response. Run this. Here are the summaries of the self-RAG and the long LoRa. It is given a summary. So let's move on to the next question. So here this code defines the URLs and the papers. The URLs list contains about 11 links to the research papers in the PDF format from the Open Review website, while the papers list consists of corresponding file names that likely represent the downloaded versions of these papers. So each URL in the URLs list maps to a specific file name in the papers list, suggesting that these names might be used to save the downloaded files. So this setup can be useful for automating the downloading process, keeping track of the files, or referencing papers by their assigned names. So we'll run this. Now, this is here to process a list of research papers by actually extracting the specific tools for each document using the getDoc tools function. It begins by importing the getDoc tools from the utils module and the path from the pathlib for the handling file names. An empty directory, the paper to tools directory, is initialized to store the mapping of each paper to its respective tools. The code then iterates through the papers list, printing a message to indicate which paper is being processed. For each paper, it calls the getDoc tools, passing the paper's file's name and its file name without .pdf extension, that would be so this function returns 2 tools: a vector tool likely for converting into embeddings for the NLP task and everything, and the summary tool which might generate the summaries of the paper. So these tools are then stored in the dictionary with the paper file name as the key and the tools as the value. So this setup enables efficient document processing, allowing for easy access to the vectorized representations and summaries of each research paper. So it's generating all the outputs. So now we'll move on. So this code creates a list called the all tools that collects all the tools from the paper to tools dictionary for every paper in the papers list. So it uses a nested list comprehension, which means it goes through each paper in the papers, retrieves its associated tools, a list of the 2 tools stored in the paper to tools dictionary paper, and adds each tool to all the tools. So as a result, all tools become a single list containing all the vector and the summary tools from every paper, rather than keeping them grouped by paper. So this approach makes it easy to access and process all the tools together instead of dealing with them paper by paper. So now, after that is done, this code actually creates an object-based index and retriever for the tools stored in all tools using the vector stored index from the Llamaindex code library that is imported from. So the object index from objects function takes all the tools and organizes them in a searchable index. The index, the index underscore CLS is equal to vector store index. This argument specifies that the indexing method should use a vector-based retrieval only, meaning each tool will be converted into a vector representation for efficient searching. So this setup allows quick retrieval of relevant tools based on similarity searches, making it useful for the tasks like finding related tools based on the user queries. So we'll run this. So now this code, that's object retriever is equal to object index as retriever, similarity top k is equal to 3, is creating a retriever object from the object index, which likely represents an index collection of data such as the documents or embeddings. So the asRetriever method converts this index into a retriever, allowing it to fetch relevant results based on similarity. The parameter of similarity top k equal to 3 ensures that when a query is made, the retriever will return the top 3 most similar results based on their relevance. So this is useful in applications like the search engines, chatbots, or recommendation systems, where retrieving the most relevant information is very important. So here the tools equal to object retriever dot retrieve is asking the retriever, that is object retriever, to find the relevant information related to the given query. So the retriever searches through the index data and retrieves the most relevant results based on the similarity. Since object retriever was configured to return the top 3 similar matches, it will return up to the 3 pieces of relevant information. The retrieved results are then stored in the tools variable, which can be used for further processing, such as displaying the information to the user or using it as an AI model. So this process is commonly used in the AI-driven search systems, chatbots, and question answering applications to fetch the relevant data efficiently. Now let's access the metadata of the third retrieved result from the tools. So we'll write tools, and within third bracket we'll write to and dot metadata, and we'll run this. So this code tools.metadata is accessing the metadata of the third retrieved result from the tools list. It stores the results returned by the object retriever. Each item in the tools contains both the retriever content and the additional metadata. So metadata typically includes the extra information such as the source, timestamp, author, or document ID, or other attributes that describe the retrieved data. So as we have known, we'll move on. So now we are setting up an AI-powered agent that can answer questions based on the retrieval information from a collection of papers. So first it imports the function calling agent worker and the agent runner from Llamaindex core agent. Then it creates an agent worker using the function calling agent worker from the tools, which takes the object retriever as a tool for retrieving relevant information, and LLM to process and generate responses. The system prompt ensures that the agent relies on the retrieved data instead of the prior knowledge. The verbose is equal to true. Setting enables detailed logging, helping to debug or track how the agent retrieves and processes data. So finally, agent is equal to agent runner. Wraps the worker inside the agent runner, making it easier to manage and execute the agent's task. So this setup basically allows the agent to intelligently retrieve and generate answers based on the predefined knowledge base, making it useful for research, document analysis, and question answering applications. So we'll better run this. So this code is making the AI agent answer a query about the evaluation dataset used in the MetaGPT and how it compares to the SWE bench. So the query function sends this question to the agent, which then retrieves relevant information using the object retriever and processes the response using the large language model. The retrieved and the generated response is stored in the response variable. Finally, we are printing the response, converts the response into a string, and displays it. So this allows the AI agent to provide a well-structured answer based on the available documents, ensuring an informed comparison between the two datasets. So it has started generating the response, and then the last step is making the AI agent analyze and compare the two research papers. There is the long LORA and the loft queue. The query function sends a detailed question, making the agent to first analyze the approach used in each paper and then compare and contrast them. So the agent retrieves relevant information using the object retriever and processes the response using the language model. So the generated response is stored in the response variable. Finally, the retrieved and analyzed answer, if you run this, can be printed or used further. So this setup helps in extracting the insights from the research papers efficiently, making it useful for their academic research, technical analysis, and AI-driven summarization. So down the line, let's conclude this course. So guys, throughout this journey of building the Agentic RAG applications, we have explored how to enhance AI's ability to retrieve, process, and reason through complex informations dynamically. We started with an introduction to understand why agentic reasoning is important in retrieval augmented generation and how it improves AI's ability to handle diverse queries effectively. We then explored the router query engine, which helps the direct queries to the right sources, making retrieval more efficient. Moving forward, we implemented the tool calling, enabling AI agents to interact with the extract tools and enhance their decision-making capabilities beyond simple text generation. Now, the next crucial step was constructing an agent reasoning cycle where we developed a system that allows the AI to process information iteratively, improving its responses based on new insights. Finally, we created a multi-document agent which enables the system to pull and synthesize information from multiple sources, ensuring more comprehensive and accurate results. Through both detailed explanations and hands-on demos, we saw how these components come together to form an intelligent agentic RAG system capable of making decisions, retrieving relevant information, and interacting with tools to enhance its functionality. The potential of Agentic RAG is vast, from personalized AI assistants to automated research tools and context-aware decision-making systems. So by mastering these techniques, you are now equipped to build and refine your own intelligent AI applications, taking retrieval augmented AI to new heights. As AI continues to evolve, integrating reasoning, retrieval, and the tool interaction will be a key to developing more capable, autonomous, and adaptive systems. Now it's time to take what you have learned and experiment with building your own agentic RAG solutions to push the boundaries of AI. So guys, congratulations on completing the Building Agentic RAG Applications course. You have taken a major step towards mastering the AI-driven retrieval and reasoning systems. Now it's time to put your knowledge into action, experiment with Agentic RAG, refine your agent's decision-making abilities, and explore the innovative way to enhance the automation and the contextual understanding. Keep pushing the boundaries of AI and making the most of what Agentic RAG has to offer. Happy coding, guys, and thank you for being a part of this journey.
Staying ahead in your career requires continuous learning and upskilling. Whether you're a student aiming to learn today's top skills or a working professional looking to advance your career, we've got you covered. Explore our impressive catalog of certification programs in cutting-edge domains, including data science, cloud computing, cybersecurity, AI, machine learning, or digital marketing. Designed in collaboration with leading universities and top corporations, and delivered by industry experts, choose any of our programs and set yourself on the path to career success. Click the link in the description to know more.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.